you all for the first lecture this afternoon.
Which in my pocket.
Jacques Tilouine. He is one of our great friends based in Paris. And he keeps coming back to India quite regularly. And now he is here to give this course on divisibility towards anticyclotomic. Thank you, Jacques.
So thank you very much for the introduction. I am a little embarrassed to give a talk about archaeological mathematics or even paleontological. But anyway, that was what I was requested to do, so I'll do it. So it's a series of 4 talks, 2 by me and 2 by Haruzo, about our work of the 90s. So the situation is we take F totally real of degree G, R its ring of integers. I denote by D the different. IF is the embeddings from F to Q bar. M is a CM field, which is a CM quadratic over F. R is the ring of integers. Complex conjugation generates the Galois group. IM is the set of embeddings. So I fix a complex embedding of Q bar and also a p-adic embedding. Our prime P will be always greater than 2. And so we consider the set of places above P inside F. And we assume the fundamental assumptions that for any I, Pi splits in M. So we choose half of these primes. So let's say P1, PR. And so of course this set has the property that P disjoint union with PC is SP of F. And we define a set of embeddings in IM such that sigma P, iota P composed with sigma is an embedding of M into QP bar, which is continuous for one of these topologies. Continuous for the PI topology for some I. And so this defines a CM type. So if we compose with iota infinity, this is a CM type. So is such a CM type is called a p-adic CM type. Actually, the p-adic CM type associated to P. And we fix it from now on. So the first part is the statement of Iwasawa main conjecture and anticyclotomic main conjecture. So we fix an ideal C in R, which is invariant by complex conjugation. So we can decompose it as a product of of ideals. So this is a product of primes of primary ideals of relative degree 1, and these are inert or ramified factors. So actually in our work, our 2 papers with Haruzo, I can be arbitrary, but in the subsequent paper of Haruzo, I must be 1. And so, well, sometimes it's, anyway, I won't say much about this set of primes. So if you like, you can assume that C is actually this product. Okay? So we consider the ray class fields of conductor Cp to the n, and we take the union. So this is the union of the ray class fields of conductor Cp to the m. So the Galois group over m is a profinite group, which can be decomposed as its torsion part and its p-profinite part. So this module is isomorphic to Zp to the power g plus 1 plus the possible defect of Leopold conjecture for the field f at p. So that could be 0, but. And this group we will denote by delta C. And of course, if P does not divide the class number of conductor C, this group delta C is just the ray class group of conductor C. But if P divides the class number, well, it's a little different. Okay, so we take a finite extension of Zp unramified hat, which is a DVR, which is complete DVR. And so using CM abelian varieties of type M sigma, we can define a pair of periods, omega infinity and omega p. So this pair belongs to C cross to the sigma times O cross to the sigma divided by R tilde cross. R tilde may be localized at P. So R tilde is the ring of integers of the finite abelian extension of the reflex field of M. So the reflex field is the field generated by the reflex trace of elements of M. And the reflex trace is given by the inverse of the elements of sigma, once, well, in a suitable sense. Yeah, diagonally, by the sigma embeddings, diagonally, yeah. So we have these periods. Oh, well. Well, maybe I could use this space now. Yes, yes. Your localization at P, yeah. So we consider a Hecke character of M from the Idel classes, such that at infinity, so for a component at infinity, it is algebraic. It is given by x infinity to the minus eta, you know, maybe from, I don't know, If I put iota infinity, I put it on the right, but this is Hilbert notation. On the right means on the left when I use the composition. Anyway, okay. So what is eta? Eta is an element of Z of IM. So that's the notion of A0 type Hecke character. To have an infinity type of this form is an A0 type Hecke character. So consider such a character. And what is yeah? But actually, for some simple reasons, eta has a specific form. It must be of the following form. It must be some integers times some integer times sigma plus summation of delta sigma 1 minus c for sigma in sigma. And this notation is an abuse of notation. Sigma is now viewed as a linear combination of embeddings inside Z of IM. So it must be of this form where n0 is an integer and delta sigma are integers. This comes from purity condition. So actually, all etas are not allowed to be infinity types. There must be a condition, namely eta sigma plus eta sigma c must be a constant, and that's the constant n0. Okay? That's purity condition. Okay, so we need to take such a condition. And to such a lambda, you can attach an L function, the Hecke L function attached to the Hecke character lambda. So it's the sum of lambda of Gothic A divided by norm of Gothic A to the S, where Gothic A is prime to the so-called conductor. There is a conductor. So for... Sorry? Yes, only in the first term, yeah. The shape of eta is exactly like that. It must be like that.
But you wanted eta sigma.
Yes, yeah. For all sigmas in sigma. Times 2 is a constant. Yeah, is a constant. Yeah, so for us, the conductors we will consider are only of the shape Cp to the m. So A will be, so A is an ideal inside R, which is non-zero. And so that's the Hecke L function. And as you know, if lambda is non-trivial, you have analytic continuation plus functional equation of the shape Ls lambda is equal to something L1 minus S lambda minus 1. So that's crucial for us. We will use that, although I won't use we use it in the paper, but I won't write down the factor here. And so we have this notion of Hecke character. And so there is a periodic L function defined by Katz. So the Katz periodic L function is an element. So it is associated for us to the CM type and to the ideal C. Yeah, the C is the Gothic C. So it's an element of O double bracket G infinity of C. And this ring can be identified to the ring of measures, measures from G infinity C, from G infinity C to O. And so with the following interpolation property, so when we have a character lambda of this type, there is a p-adic avatar. Notion comes from Vail, who was a big India lover. Lambda hat of x is defined to be, if you like, iota lambda of x outside p times, outside infinity times xp to the minus eta iota p. So this is the p-adic avatar of lambda. And this p-adic avatar gives rise to a continuous homomorphism from Galois to some p-adic tension of QP. And so this is a continuous function. So you can integrate against this measure, which when we view it as a measure, we write mu equal mu sigma c instead of L. So you can integrate this function, continuous function, against this measure. And the property is the following, interpolation property. For all characters whose infinity type is the following, we get the Katz L value. So the Hecke L value, sorry. So the integral along the Katz measure of lambda hat gives rise to the Hecke L value, except that it's not for all characters, it's for the so-called positively critical characters. So lambda is positive critical. If you write, if the infinity type eta is actually, so now I am more precise, minus M0 sigma minus D times 1 minus C. And so M0 is positive, no, sorry, is at least 1. And D sigma, so this is D equals some D sigma, sigma for sigma in sigma. D sigma is greater than 0. So that's the notion of positive critical. And you have the notion of negative critical. It is same with M0 less than 1 and D sigma greater than 1 minus M0. Okay, so that's positive critical, that's negative critical. And so the interpolation formula involves only the positive critical. So the integral of a positive critical Hecke character d mu over G infinity C divided by omega p to the power M0 sigma. M0 is this one, plus 2D. So D is a combination of integers, but you can view it as a character of O cross. Okay, it's a p-adic character. So this defines the p-adic character of O cross. So it makes sense to form this product, and so it will be given by the L value L0 lambda, or 0, divided by omega infinity to the same power, except that here there is a iota p and here there is a iota infinity, M0 sigma plus 2D, times some factor, also there is a power of pi. So pi to the d means just the power, the pi to the sum of the integers, sum of the d sigma, okay, times some algebraic number, a of lambda, which it's an explicit constant in Q bar, which depends only on the Euler factors of the Hecke L functions at P, at C, and at infinity. Okay, so that's the interpolation formula for all positive critical. And actually, there is an interpolation formula for negative criticals, and it gives rise to a functional equation. So that, which one?
This one. XP, next one.
Yeah, XP is the P component. P is the P for P is fixed from the beginning. Is the prime we fixed from the beginning. There is a prime P which is fixed. No, it's a rational prime. Yeah. So this is a semi-local component. This means, yeah. So that's why you can let this kind of character act on these semi-local components. Okay. So there is also another measure, mu star, which is good for interpolating negatively critical Haeckel characters. I am very brief about that. And there is a functional equation. Unfortunately, it's very important for us. So if you have a positive critical character, lambda, you can define a negative critical character by the formula. So lambda cross of x is the adelic modulus times lambda of x to the minus c. And this one will be negative critical if this one is positive critical. And then there is another measure, mu star, which interpolates the p-adic avatar of these negative critical over the same power of omega p, involving the infinity type of this one, of course. And that will be some a of lambda star of L0 lambda star divided by omega infinity to the power corresponding to the infinity type. And there is a functional equation which I write, p-adic functional equation. So I write it as L star, which is this thing viewed as a series. L star is equal to V times L, where V is a unit inside O double bracket G infinity C. So that's the functional equation. So it's a lot of calculation, but Katz, yeah. Katz, we generalize, so in Katz's paper, the auxiliary ideal C is 1. So you have to redo the calculation for C, for the auxiliary ideal C. But yeah, it's in Katz. Plus, not at all. No. Lambda star. Yeah, but the relation is, well, no, the omega infinity is the same. The omega infinity is the same. It depends on some auxiliary abelian variety. You define omega infinity and omega p to some power. Okay. Yeah. Oh. Yeah. If you want to define omega infinity, if you want to study these abelian varieties and define the complex periods, yes, it is in Shimura Taniyama. The p-adic period is defined by Katz. You need some. That's why you need the ring O. Actually, you need the ring ZP and ramified hat to define omega p. No, but that's not something I wanted to focus on. I mean, I want to mention that's where it comes from. It comes from there, but so now we assume that C the auxiliary ideal is invariant by complex conjugation. So there is an action. There is an action of the complex conjugation on this. So we consider the plus part, which means the part on which, so this is the set of sigmas on which C acts by the identity. Okay. And we decompose the plus part. So we can, as I said, we could decompose this as delta C times W. And both of them are stable under the action of C. So since P is odd, you can decompose this as plus part and minus part. And it turns out, if you use class field theory, that this is rank 1 plus S, and this is rank G. The minus part has rank G. This one we don't decompose because the order is not odd. So we consider the sub G infinity plus. It's a sub. It's not a factor, but so there is a decomposition like this for the plus part. Sorry. The plus part can be decomposed like this. And now we consider the quotient, okay, and that will be the anticyclotomic quotient. So GAC is the quotient G infinity C divided by G infinity plus C. And so it decomposes as delta CA times W minus. So this is ZP to the G, and this is the quotient of delta C modulo delta C plus. And it has, therefore, the property that the characters of this group, if you have a character of this group, this is a finite group. This is a finite group here. So if you have a character of this finite group, if chi is like this, there exists a character of delta C such that chi is psi C divided by psi, which means psi of sigma C divided by psi. This is conjugation by C. So that's easy because of the definition of delta plus as the invariance. And so given a chi, we get a psi. And that's very important. So this is a so-called anticyclotomic character, finite order character. And it gives rise to a character psi also. And so we introduce Iwasawa algebras. So the big Iwasawa algebra is lambda O double bracket W, and the anticyclotomic Iwasawa algebra, lambda minus, is O double bracket W minus. And so, of course, there is a projection. There is a projection pi coming from, you just divide by W plus, okay? Take the minus part. There is a surjective projection, and we choose a section. It's not exactly a section, it's a quasi-section of lambda minus to lambda. Namely, if you have a W minus, an element W minus inside W minus, you send this element to W minus to the power minus 2. So it's not a section, it's a quasi-section, but that's what we have to consider. The quasi-section of pi. Okay, now I draw a picture which I could have drawn before the beginning. So you have the real field F, you have the quadratic extension M, you have the ray class field M infinity, CP infinity, you have n sigma of m Cp infinity, which is the maximal, and you have the Galois group here, x sigma C. So this is the maximal sigma ramified P abelian extension of M Cp infinity. And so the Galois group here is a pro P, of course. And here you decompose into W. So here you have G infinity of C. Here you have W. Here you have delta C. So this field is M prime, say, delta C. And you take, so now you consider the invariance by G infinity C plus. So you get a field which I call M anticyclotomic. And you take the subfield here fixed by delta C plus. You get, oh no, this one is M infinity anticyclotomic. Here you get M anticyclotomic, so it's a finite extension of M. And this has Galois group W minus. And here, so this is the cyclotomic, the anticyclotomic extension of MA, and MA has Galois group delta C anticyclotomic. So here we fix characters, and so we consider the module n sigma of M infinity A. And the Galois group is the anticyclotomic Galois group. And so this is a module over this group, which is G anticyclotomic C. And this one is a module over this thing. So if we fix a character here, we have a structure of lambda module for this module, for the chi part, for the part chi part of this module. And similarly, if we fix a character here, we have a structure of lambda minus module for the chi part of this module. So the Iwasawa main conjecture concerns for any character chi here, concerns the structure of a lambda module of the chi part here, and which is a finitely generated lambda module. And actually, under the so-called weak Leopold conjecture, it can be proven to be a torsion lambda module. And similarly for the other one, for the anticyclotomic one. So, sorry. Ah, okay, it can be, okay. But if you assume weak Leopold, it's okay. I think if you assume that if you climb these towers, if you assume that the defect of let's say let's consider, for instance, sorry for this one. If you assume that for these extensions M C P to the n, if you have that the defect of M C P to the n is big O of P to the degree, so degree is I don't remember what the degree of this field is, -1, okay. So degree of M, yeah, degree of M actually. If degree of M, so degree of M is 2G. So yeah, I'm not completely sure whether it is G or 2G. If you assume that for all N, the module is torsion. That's weak Leopold. Of course, Leopold is that this is 0. But if it is big O of one less of, I don't remember whether it is the the dimension, this is in our paper. So anyway, there is one less, definitely something. And so if you assume that, it's torsion. Yeah, okay, but yeah, okay, so that's completely another proof. So a priori in our paper, we stated. Okay, it's equivalent. Okay, maybe, okay. No, yeah, but in that case, it is true. Okay, I don't know whether it is equivalent, maybe, but anyway, so we assume what you need to say that, so we have two statements that X sigma C chi for chi in delta C hat, and similarly for chi in delta C anticyclotomic hat X sigma C anticyclotomic chi are, so this is lambda torsion, finitely generated lambda torsion, and this one is lambda minus torsion. So we assume that. We don't need that. If it is not torsion, our theorem is true. It says that something divides zero. Okay. Yeah, okay, I understand. But even in our paper, we didn't need to assume that it's torsion. Okay, but anyway, so that's correct. So and lambda torsion. So there is a characteristic power series which we denote by F sigma C chi, and here F sigma anticyclotomic C chi. And on the other hand, there is this Katz p-adic L function, this L, which maybe we could denote as L sigma C, and we can take the chi part, okay? And so the Iwasawa main conjecture is that up to a unit in lambda, so I write this and lambda, these things are equal. So this is Iwasawa main conjecture, okay? And for the anticyclotomic part, you have the anticyclotomic specialization pi of the, so maybe we denote by LA. So I take the pi of L sigma C chi, but chi for now is anticyclotomic, and that I denote by L anticyclotomic chi sigma C, and the anticyclotomic main conjecture is that these things are equal in lambda minus, in lambda minus. So that's the anticyclotomic main conjecture, and that's the main conjecture, Iwasawa main conjecture. Okay. So actually, what we do with Hida is to prove a divisibility towards this conjecture. So instead of proving that they are equal, we prove that this divides this. And actually, in the ring lambda minus, there is one special prime which we cannot treat, namely the prime P. P is one prime in lambda minus, where we cannot prove that this divides this. So we prove it in lambda minus inverted, where P is inverted. So the main theorem is that L sigma C anticyclotomic chi divides F sigma C anticyclotomic chi for all chi in delta anticyclotomic C, but in lambda minus of 1 over P. Okay? Sorry? No, I don't think so. No, it's automatic. No. It's automatic because, yeah. And so what is the strategy? So you see, as I said, this anticyclotomic chi can be written as psi c over psi. And so we will introduce, as associated to psi, an element h psi in lambda. Lambda, not lambda minus, okay? And since we work we want to study things in lambda minus, we will prove results by applying our quasi section. Okay, so the strategy is in two parts. We prove that the quasi section of the anticyclotomic p-adical function divides h psi in lambda, and actually lambda 1 over p. And second, we prove that h psi divides, actually the second divisibility is in lambda, so divides v of hm over hf times f sigma c a chi in lambda. And here, this is the class number, and here the class number. So in the second part, we can treat the p part, but in that one, no. Okay, and so I have to say a word about h psi. This belongs to lambda minus. This is the quasi section. This belongs to lambda. So this is in lambda. This is defined in lambda. So we go to lambda, we prove this, and then we prove this in lambda again. Okay, and therefore then you can remove the v's and no. Well, the main conjecture implies the anticyclotomic main conjecture for those characters, yeah. Yeah, so one word about the h psi. We will need to come back to it anyway. So if we have an ideal n in ring R, in F, you have the notion of the nearly ordinary Hecke algebra of Hida of level auxiliary. So nearly ordinary Hecke algebra of auxiliary level n, cuspidal, of course, nearly ordinary cuspidal Hecke algebra of auxiliary level n, of course, for Hilbert modular forms. Okay, we are talking about Hilbert modular forms over F. So I will come back to some details. But anyway, what is important for us is that there is a torus, Tp of n, which maps actually to this Hecke algebra. This is the torus of so-called diamond operators. So if you like, it is a diagonal torus inside GL2 of RP times well, actually, we don't need to go that way. Rp times R modulo n. Okay, so if you like, it's the inverse limit of R modulo n p to the m cross two copies. Well, and to be actually, it's a little more complicated. It's this, but modulo something. This Well, R is the ring of integers of F. And this torus, you see, it is, if you like, it is the diagonal torus over, it is the diagonal torus as I wrote. You take this torus, but you divide by the subtorus, which is the center. How can I say that? Well, you take the R point of the center, and you take the p-adic closure inside this diagonal torus. So it's AB, but you neglect the ZZ, which come from units. Okay, you divide this torus by epsilon, epsilon, and even the p-adic closure. Okay? So it's a torus which has rank G plus G minus G minus 1 minus S. Okay? G plus G minus G minus 1 minus S defect of Leopold because of this p-adic closure, and that's G plus 1 plus S. So that's a nice coincidence that it is also the rank of our Galois group. Here we are over F, okay, but it's also the rank of our Galois group over M. Okay, and you let it act, so it maps to the units. It acts on modular forms. So the action is denoted maybe by T of AB, and this T of AB is the double class of something, U infinity, AB, U infinity. And what is U infinity? So actually it means that at each level n, you consider the group UN of matrices G in GL2 of R hat, which are congruent to 1 star 0, 1 modulo P to the M, and maybe also N if you like, but it's not that important, modulo N. So you take this group, and this condition is very strong. This group is very small, and that's why it is called nearly ordinary. If you allowed this kind of condition, then the group would be bigger, and then it would give rise to nearly ordinary, to ordinary Hecke algebra, which is much smaller. And unfortunately, the modular forms we need to use are nearly ordinary, but not ordinary. So we really need the nearly ordinary Hecke algebra. So you take this group, you take the Hilbert modular forms of this kind of level, and you take all of them, and you take the Hecke algebra which acts on them, and you use some nearly ordinary projection, and you get this nearly ordinary Hecke algebra, which has no weight. Weight disappears when you take the limit. So this is the limit when you grow modulo all level mod P to the M. And so, so you have this nearly ordinary Hecke algebra with action of this torus, and therefore you consider a decomposition of this torus into pre-profinite, P-profinite part, which has rank G plus 1 plus S, same rank as before, times something finite, which does not matter. And so you have an action of the Iwasawa algebra lambda 0 equal O double bracket, we take coefficients in O, double bracket W0. So we introduce this Iwasawa algebra of the diamond operators, and it is, so this is a lambda 0 algebra, and the main theorem of Hida's paper in the Iwasawa volume is that this is finite torsion free over lambda 0. So this big Hecke algebra, H nearly ordinary, is finite torsion free over lambda 0. Okay. And so we are interested in families. What are the families of nearly ordinary Hilbert modular forms? Well, they are basically they are the choice of height 0 prime ideal inside this ring. If you choose a height 0 prime ideal in this ring, if you consider the quotient, by this prime ideal. It's an extension. It is over 0, of course, in lambda 0. Okay, you have H nearly ordinary, you have lambda 0. If you take such a prime, it is over 0. So this I contains lambda 0, and it is finite. It's a finite extension, and the projection is what we call a Hida family. This is a lambda 0 algebra homomorphism, and this is finite, torsion-free. So it's a finite extension, actually, torsion-free, finite. And this map is the Hida family. So if you gave, lambda, I don't know. But so that's the notion of Hida families, which are nearly ordinary. And we will use some Hida families like that. But anyway, when you have a Hida family, you can define a congruence module for the Hida family. And that's a simple diagram. And so here we will use the congruence module for a CM-type Hida family given by psi. To psi, we will attach a Hida family for the H nearly ordinary. And to this family, we will attach a congruence module. And this congruence module has a characteristic power series. And that will be our H psi. So in general, when you have a family, you have a congruence module. I can explain just by a diagram. You have H nearly ordinary, you have one family that you choose, and you have the rest, which means that this is a product, if you tensor by the field of fraction, if you tensor by the field of fraction of lambda 0, K0, it becomes the product of this by some other algebra, because it's semi-simple. This is semi-simple, okay? This is semi-simple. So you have some other algebra that we denote by H prime. So this is the image. We take the image of this inside that. And so you have a diagram like this, and basically these are the other families than lambda. And so the congruence module is the largest quotient that you can make here by some ideal, eta lambda, such that this diagram commutes. So this is the congruence module of lambda. And here we will have, so this eta lambda is an ideal in I. And in some cases, for instance, if by any chance this ring is factorial, if I is factorial, for instance, if it is an Iwasawa algebra, if it is factorial, then this ideal has a height 1 envelope, which is principal. So if you replace eta lambda by the intersection of the height 1, the height 1 components, so the localizations, if you want the localizations at height 1, then this is principal. And then you call it the characteristic power series of the congruence module. Okay, so when you have a family, you can attach to it, if the ring I is principal, is factorial, you can attach to it a specific element up to unit. But we work up to unit, we prove divisibilities only, okay? So, and we will do that for a specific Hida family, namely I will give more details next time, but here the ring I will be the ring lambda. Lambda is the one using the Galois group, okay? Which is different from lambda 0. And actually there is a map from lambda 0 to lambda, which is given by class field theory. And we will define a family here, which is called theta psi star. So star because it comes from a family of modular forms, theta psi, which are given by psi. So it's a family of CM modular forms, of CM Hilbert modular forms for F over F. Associated to psi. So we will define this family, and so it will be lambda 0 algebra homomorphism. And so this is factorial. So there is a congruence series H psi belonging to lambda, of course, up to units. It's not well defined, it's defined up to a unit. Well, I will come back to this next time, I think. So now we have the object. And so what are the ingredients of the proof? So there are two things to prove. So let's say 1 and 2. 1 was the one. So sketch of proof. And before really going to the sketch of proof, we need to list the ingredients which will be needed. So sketch of proof, let's say for the moment of 1. So 1, I remind you, is the divisibility relating the Katz p-adic L function, the anticyclotomic specialization of the Katz p-adic L function, and the congruence power series. So to prove this, and the divisibility will hold in lambda of 1 over p. And so what are the ingredients we need to introduce? 3 ingredients. Katz p-adic L function, CM Hida families, and Rankin-Zellberg p-adic L function, and actually it will be applied to 2 CM families. Rankin-Zellberg p-adic L function, which will be applied to 2 families, namely 2 CM Hida families. And so we will see the arguments next time. So yeah, ingredients and arguments to prove a theorem. That's what you need usually. So ingredients, arguments is relation between this Rankin-Zellberg applied to 2 CM families and Katz p-adic L. And then there will be a mu invariant argument. The strange part of this mu invariant argument is that this is why we cannot treat the prime p. Should be exactly how to treat the prime p. But... Okay. So actually, I wanted to say something about the Katz p-adic L function, about its origin. Actually, what is the idea? The idea is that the Hecke L function of a Hecke character is related to Eisenstein series evaluated at CM points. Okay, that's the key word. LS is related to Eisenstein series evaluated at CM points. And so then Eisenstein series give rise to p-adic measures. That's also cats, but it's kind of easier to understand than this gives rise to measure. But then the measure associated to this, the p-adic measure we are looking for, will just be a finite linear combination of Eisenstein measures evaluated at CM points. So as usual, when you want to construct a p-adic object, you look carefully at the Archimedean construction and you try to imitate it p-adically. So this sentence is what you need to imitate p-adically. So I just go to the beginning of the... You choose a finite set of complete set of representatives of the class group of M. These are fractional ideals inside M, and you assume they are prime to CP. Now, if we take any integral ideal A, non-zero, in R, we can write, if we want, as something times AJ minus 1, and something principal, and this principal thing, alpha, will be in AJ minus 0. Okay? And so you rewrite the definition. So the definition was this. You rewrite as sum of lambda AJ minus 1, finite sum, times summation of lambda of alpha divided by norm from M to Q of alpha to the S, where alpha runs into AJ minus 0 modulo R cross. Okay, that's the starting point. Because this you will interpret as the special value of an Eisenstein series, more precisely of a derivative of an Eisenstein series. So you introduce lambda finite of alpha, because you see the problem is that this function is not of finite order. So you modify it slightly such that lambda depends on alpha, is a function on a finite group. So here it's not a function on a finite group, but if you modify it as follows, you consider lambda of alpha times alpha to the dc over alpha to the d plus m0. What is d? Yeah, maybe correct. I think, yeah, maybe correct. Like this, if you consider this new function, these factors, it's a function on the elements of m c p to the m, elements of m prime to this, modulo the elements which are congruent to 1 modulo, I don't know how to write this, it's a bad notation. This is completely different from before. This means the elements of M which are congruent to 1 modulo these things. And this is a finite group, okay? And this finite group is very simple. Basically, it is R over C P to the M cross. So this function becomes a function on a finite group. But of course, you have to introduce this inverse. And this will give rise to a derivative in the sense of Maas-Shimura, the Maas-Shimura derivative of an Eisenstein series. And then you evaluate it at some value. Which value? Well, you see here, we... just a word, and I won't do all the calculation, but I think it's kind of interesting. You see, you write the ideal AJ, because after all, alpha runs over AJ minus 0. So you write the ideal AJ as AJ star plus BJ times some delta. So what is delta? Delta is basically the square root of minus d. So delta is an element in R such that the complex conjugate is minus delta. So if you like, you can take square root of the opposite of a totally positive element of F. Okay? Something like that. And these are ideals. These are ideals. So different has been introduced, so I can tell you what is AJ star. It's B minus 1, D minus 1, AJ minus 1. So these are ideals in F, in F, yes, fractional ideals in F, fractional ideals in F. You can write AJ like that. This does not belong to F, of course. It belongs to M. And then you apply, you see, the property of sigma, of the set sigma, is of course that if you restrict these embeddings to F, you have all the embeddings. Okay? So if you take delta and you apply sigma to delta, you find something inside C of sigma, but if you think a little, it is in the Hilbert half plane, half space, h to the if, because of course the imaginary part of all the embeddings of delta will be strictly positive. I mean, that's what you choose. I'm sorry, maybe you. And so that's a point in the Hilbert space, and that's a CM point because it is given by an element of M. That's the CM point at which you evaluate your Eisenstein series in order to find these values. So after some calculation, a very little calculation, you can see that L0 lambda can be viewed as a finite sum of these lambda aj minus 1. Then you will have the mass Shimura differential operator to the d. It comes from this factor here, which has to come if you want something finite order. And then some Eisenstein series, which is given basically by this lambda finite function by a partial Fourier transform of this Eisenstein series. So you will get some Eisenstein series, let me see, evaluated at this point, sigma of delta, and this ideal AJ. Yeah, okay. Oh, well, this, okay, I'm sorry. Z, and then you take this derivative and then you apply Z to be sigma of delta. You need, well, okay. Sometimes you don't need this derivative in case D equals 0. Okay, but, sorry? The norm of AJ is exactly, this is the Eisenstein series. This is the Eisenstein series. The norm of AJ, this norm of alpha is, here. Oh, okay, maybe, yeah, okay. Maybe there is a norm of AJ minus 1, minus S, but I take S equals 0. Okay. Okay. And so, okay, and these objects, and the Eisenstein series maybe has weight M0, I'm not completely sure what is, yeah, M0. Well, and it depends on J, yeah. And so these Eisenstein series give rise to a p-adic measure on some torus. And yeah, so you can define p-adic measures, EJ, so on RP cross times R over F cross times RP cross times R over F cross with values in the p-adic modular forms with some auxiliary level C, which is absolutely not the previous C. But anyway, C is defined by being the fractional ideal such that lambda 2 of R over R is D minus 1, C minus 1. So, and what is F? F is F intersection R. So F was the part of relative degree 1 in, so this is an ideal in R. Part of a relative degree 1 in the conduct, in auxiliary level C. Yeah, okay, so this construction, interpolating these Eisenstein series. So here you keep the variable. So you take a measure with values in p-adic modular forms. So, but then you can evaluate these p-adic modular forms at this point. And of course, this operator has a meaning in the space of p-adic modular forms. It's a Ramanujan operator, differential operator, so it acts on p-adic modular forms. This operator has an avatar, p-adic avatar, in the space of p-adic modular forms. So you can apply this operator, and then you can apply to this measure the specialization at a point that's x values in O. This is why I take O to be a finite extension of ZPN ramified hat, because you have, for instance, here, so some extension of ZPN ramified hat. Okay. And so I don't want to say much more on the construction of the Katz p-adic L function. So it will be defined as a finite, so basically the Katz measure is defined as the sum of these things times these measures. Well, what is the relation between this and G infinity C? It's class field theory. Okay, I remind you that RP cross times RP cross is just RP cross. And so basically you can see this inside the Galois group by class field theory. And so you can consider the push forward of these measures to the Galois group, here. So that's, maybe there is a push forward. And that's the definition of this measure. Now, just a word. So the next, I wanted to be a little more precise on the, so the second ingredient is CM Hida families. So I'm not sure I have time now, but I will be a little more precise about these objects in order to define the family theta psi from the nearly ordinary Hecke algebra to this extension of lambda 0. So that's the next thing I want to do, but maybe not now. I stop at 4. Oh, I just stop now. I stop at 4.
Yeah.
Yeah, well done, yeah. Done or 15 more minutes? Next time, yeah. At the beginning, the p-adic functional equation? Yeah. Yeah, because there is a classical functional equation between L0 lambda and L1 lambda minus 1. But L1 lambda minus 1 is L0 lambda star. As I said, if you take the positive critical points, lambda, then you can define lambda star, which is negative critical and which is, but so the operation of passing from lambda to lambda star can be interpreted as a p-adic variable change. So you had lambda, which was M0 sigma plus D times 1 minus sigma, and lambda star, I'm not sure I can remember everything, but so lambda star is basically norm times lambda of x minus c, norm of x times lambda of x minus c. So this operation, so you see, you have W has two variables, can be written, I wrote it in one way, but you can also write it as, well, I'm not completely sure I will say something correct. No. Let me see. Yeah, why not? Because Rp, as I said, can be written as R sigma times R sigma C cross, and this is Rp, and this is Rp cross. So basically, you exchange these variables, you take a -1, and you make a shift, and this sends you from positively critical to negatively critical. So it means that if you change the variable in the negatively critical, you get the positively critical. So it makes change, it makes sense. So you had the notion of integrating lambda hat d mu and integrating lambda star hat d mu star. Those are, so if you make a change of, and of course this interpolates the L0 lambda, this interpolates the L0 lambda star, but these are the L1 lambda minus 1, and so it's related to this by functional equation. But there is a map sending those to those, which is a change of variable in W. Oh, it's not a unit, it's a... sorry, this one, yeah. Yeah, so this one you find by comparing, so you take a lambda hat, you write the formula that you get, you write the corresponding lambda star hat, you write the formula, and then you compare using functional equation, and what remains is a unit. It's not a very complicated calculation, actually. If C is 1, it's maybe 3-page in CATS. Yeah, we just have more Euler factors to deal with because we have the Euler factors at C. But
so this time we know functional equation, one variable periodic function. In one variable, there are no functional equations.
One variable, you mean yeah, there is a functional equation. No, here I am talking about changing. There is a function.
I thought this is. You go from negative to positive.
Ah, okay, yeah, okay. You can, instead of saying that you are interpolating L1 minus n chi, you can say you are interpolating Ln chi bar times pi to the minus something, and yeah, it is the same. Yeah,